Hello, my name is Nick, and I'm going to present our work on a persistent homology-based topological loss function for multi-class CNN segmentation of cardiac MRI. We are concerned with the accurate segmentation of short-axis CMR images, our task being to separately label the blood pool cavities of the right and left ventricles and the left ventricular myocardium. The resulting segmentation serves a wealth of downstream applications, including the quantification of ventricular volume. However, these segmentations also facilitate advanced forms of 3D visualization, such as might be used in image-guided intervention and have research applications within biomechanical modeling. Thanks to the popularity and development of deep learning methodologies, recent years have seen significant progress in attempts to automate this task. Despite this progress, CNN segmentations frequently exhibit nonsensical errors that violate the most basic properties of the target anatomy, including its topology. The example shown here includes a spurious right ventricular component and a gap in the toroidal cross-section of the myocardium. These errors are a consequence of the most popular schemes for CNN optimization, which use loss functions such as cross-entropy or the dissimilarity coefficient. These act in a pixel-wise fashion, rendering them insensitive to the extended spatial features that would otherwise characterize anatomically sensible segmentation. To address this limitation, authors have sought to leverage prior information concerning anatomical shape and arrangement. The combination of CNN segmentation with active contour refinement and atlas-based methods have both been applied to this task. However, such approaches are limited in their ability to accurately segment the wide range of anatomy encountered in the clinic. Instead, Octay et al. Sought to inject prior information directly into CNN optimization using a compact representation of myocardial anatomy learned from the ground truth training data. However, it is difficult to ascertain the extent to which latent features are truly related to anatomical shape or topology as claimed. Observing that such an approach may still yield implausible results, Panchot et al. Used a constrained rejection sampling procedure to augment the latent space, only selecting examples that satisfied 16 anatomical criteria. However, a limitation of this approach is that it is biased on the available training data. As a result, it is unclear how this approach might treat an out-of-sample test case, perhaps one that exhibited significant pathological variation. In our work, we observed that the implausible CNN errors described often violate anticipated label map topology. We exploit this observation as our source of prior information. In contrast to previous work, rather than relying on a learned representation of anatomically plausible segmentations, we are able to leverage an explicit topological prior. To do this, we adapt existing tools from the field of topological data analysis, presenting a novel topological loss function for multi-class segmentation. We will show that this loss makes a significant improvement in predicted segmentation topology. I'll now talk through some of the theoretical aspects of our approach. In 2D, the topology of an object is characterized by the first two Betti numbers, B0 and B1. Respectively, these count the number of connected components and the number of holes which compose the object. If we consider the three foreground classes in our task, the Betti numbers for the right and left ventricular cavities are 1, 0, both being made up by single connected components without any interior holes. The myocardium is different. In short axis view, the myocardium takes on the appearance of a ring, hence its Betti numbers are 1 and 1. This description, however, is only part of the story. Whilst it faithfully represents the individual classes, it fails to capture their interaction. Instead, a topological description of a set of 2D objects is achieved by considering not only individual classes, but also all pairs of foreground labels. The resulting description additionally specifies that the right ventricular cavity is bound to the myocardium, which in turn entirely surrounds the left ventricular blood pool. Notice that this topological prior reflects a global property of the data in opposition to the measures of pixel-wise accuracy. At first sight, however, it is difficult to see how such a constraint could be made differentiable so as to be consistent with gradient-based learning. To bridge this gap, we use a tool from topological data analysis called persistent homology. For our purposes, this analysis is best understood by considering the persistence barcode shown on the slide. This reflects the topology of a series of snapshots of the data, each created by thresholding the probabilistic segmentation at some value between probability 1 and probability 0. As the threshold changes, the barcode tracks the evolving topology of the snapshots that result. At each threshold, the topological features are represented by bars. Solid bars count the number of connected components, open bars count the number of loops. The length of each bar characterizes the lifetime or the persistence of that topological feature. Finally, the persistence barcode has the property that it is robust to small perturbation and is consistent with gradient-based learning. I'll now describe how we use the persistence barcode to build a topological loss function. In common with previous work, we examine the topological features of the barcode and compare their lifetimes against a prior specification. Consider the barcode for the probabilistic segmentation of the paired right ventricle and myocardium classes. We anticipate that the right ventricular cavity is bound to the myocardium, which itself is a loop. This makes the Betti numbers 1 and 1. In the language of the persistence barcode, our prior expects one solid bar and one open bar. As shown in green, these features are clearly present in the barcode. However, as shown in red, we also observe a number of spurious topological features. In its formulation, the topological loss seeks to maximize the lifetime of the features that match our prior and minimize the lifetime of those which do not. To adapt this formulation for use in the context of multi-class segmentation, we consider barcodes extracted for all foreground classes and all pairs of foreground classes. In the equation, we make this clear by summing over classes I and J. In our work, we deploy this multi-class topological loss in a published CNN post-processing framework. In this scenario, we assume that conventional pixel-wise CNN optimization achieves a result which closely matches the ground truth with respect to spatial overlap, but that there may be a number of relatively small topological errors. Given the success of CNN-based approaches to short-axis segmentation, we think this assumption is fair. To correct topological errors, we use the topological loss to adapt the parameters of the pre-trained CNN. Please note that we do this individually for each test case, so in some ways the procedure could be described as test time adaptation. The topological loss will encourage changes in the predicted segmentation that modify its topology to match the topological prior. However, given that topology is a global property, there are many potential changes that are consistent with this objective. To limit test time adaptation to the minimal set of changes needed to refine segmentation topology, we introduce a similarity constraint between the raw unit prediction and the result of topological post-processing. Here we show the final post-processing loss, which is optimized iteratively. For our experiment, we used a subset of the AC/DC training set, selecting the 3 mid-ventricular slices from each phase of the cine. 450 training and validation images were used to train a standard unit using the cross-entropy loss. We then apply different post-processing operations to the 150 held-out test images and compare their performance. We considered 2 baselines. The first was the segmentation predicted by the unit without further post-processing. The second was the result returned by connected component analysis, keeping only the largest component for each class. We compared these against 2 flavors of multi-class topological post-processing. One considered topological priors for individual classes only, representing a naive extension of previous work. The second considered topological priors for both individual and paired classes, in other words, our full implementation. Here are the results. In the table, we show overlap performance and in particular the change in dice score associated with each post-processing method. We also show the topological accuracy of each approach as the proportion of test cases for which the predicted segmentation returned the correct topology. Notice that even in a problem and dataset that appears well suited to being tackled with a CNN, almost 15% of unit predictions contain topological errors, and that half of these were not resolved by connected component analysis. However, the headline is that of the 4 methods, only multi-class topological post-processing returned a segmentation with correct topology in all cases. This improvement was significant compared with connected component analysis only when priors for both individual labels and paired labels were taken into account. Finally, notice that the improvement in topological performance was achieved without degradation in spatial overlap. When coupled with the high statistical capacity of the CNN, our multi-class topological loss function enables correction via expressive changes that cannot be achieved by rudimentary methods such as connected component analysis. This approach explicitly leverages topological prior information without depending on its appearance in training data. This makes it suitable for a wide variety of multi-class segmentation problems and training datasets of variable size. However, it must also be remembered that this approach relies on the specification of the prior itself. This might not be straightforward in all cases. We also recognize that topology is just one aspect of anatomical plausibility, and that other aspects which cannot be described explicitly, such as anatomical shape, are equally as important. Our future work will seek to understand the limits of our approach with respect to the fidelity of CNN-based segmentation, whether it can be applied within weakly supervised learning, and extending its application to more challenging targets. Thank you for watching and listening.